In this section, we're going to tie together a bunch of the previous sections that we've been looking at hypothesis testing. And we're going to finally be able to start determining whether or not a hypothesis is a valid or invalid hypothesis. Let's get started. Okay, quick review problem. We did an example like this in a previous video. It says to use a significance level of alpha equals 0.01 to find the critical z-value for the alternative hypothesis. H1 gives us p, little p, the proportion is bigger than 0.5. So a couple of things I want you to notice about this before we get started in doing that review example. The alternative hypothesis here is a one-tailed, it's actually specifically a right-tailed test because our p is greater than 0.5. So that's why you're seeing this region over here on the right. Secondly, if our alternative hypothesis is H1 is p is greater than 0.5, that means that our null hypothesis would be the one with the equality. P is less than or equal to 0.5. So when we're sketching the graph of right-tailed, left-tailed, or two-tailed, we use the alternative hypothesis. But what we're actually going to be testing for, getting results for, is the null hypothesis. And we'll come back to that quite a bit. So using our significance level of 1% or 0.01, what we did was we looked up 0.01 on the standard normal distribution chart, and we got, actually what we did is 1 minus 0.01, and we got 0.99, and that gave us a critical z-value of 2.33. So our critical value of 2.33 is right here. It's the value that separates the critical region in blue from the rest of the graph. So here's what's going to be happening. For the rest of this section, we're going to be figuring out whether or not our data, which will tell us our test statistic, puts us in the critical region. If we're in the critical region, we are going to reject the null hypothesis in the critical region. But if we're over here on the left-hand side, not in the critical region, then I would love to say accept, but we don't say accept. We say we fail to reject the null hypothesis. Okay, so let's get started practicing that. Let's kind of keep with this same example. So I still would like to have from the previous example a significance level of 0.01, which meant that our critical value was 2.33 from the previous page. But now let's look at this new part. Consider the claim of the XSort method that we were talking about previously of gender selection, increasing the likelihood of having a baby girl. So if it increases the likelihood, that's where we get our alternative hypothesis is the proportion is bigger than 0.5 because it's bigger than 50% chance in this, according to this claim, that we would have a girl. Suppose a sample data resulted in a test statistic of 3.21. So here's what that would mean. That would mean this. If we had plotted our 2.33 critical value, which I'll use CV for short, and we had this value here for the critical value. Notice that our test statistic, z equals 3.21, is larger than 2.33. Let me write test statistic. Z equals 3.21 is bigger than 2.33. That puts us somewhere in the critical region, that means that we're going to reject the null hypothesis. Okay, so remember our alternative hypothesis from previously was we had H1 is P is greater than 0.5 because it's increasing the likelihood of having a girl. That meant that our null hypothesis is P is less than or equal to 0.5. If we are rejecting the null hypothesis, that means that this claim, the opposite, may be true. So it's possible that the gender selection method XSort is increasing the likelihood of having a baby. One follow-up question to this before we move on. What if our test statistic was not 3.21? What if it was 1.65 instead? Well, 1.65 on the z-axis down here would put us over here. 1.65 is not in the critical region, which means we would fail to reject the null hypothesis. So, in other words, we fail to reject the null hypothesis. The null hypothesis could actually be true. So what you're looking at is we're comparing our critical z-value that we got from our significance level to the test statistic that we got from our data. If the test statistic puts us in the critical region, we reject the null hypothesis. If the test statistic puts us outside of the critical region, we fail to reject the null hypothesis. Let's look at this a slightly different way. Okay, so instead of looking at the test statistic and the z-value, we could also look at what we call the p-value. So here's what the p-value tells us. The p-value, now this is a capital P, by the way, notice, not a lowercase p. This capital P value gives us the area to the, in this case, the right, because it's a right-tailed test, but it could be to the left of the test statistic. So the region that we have graphed here is our critical region from our alpha. So remember, this was for alpha equals 0.01. That gave us a critical region. Whoops, I lost my pen. That gave us a critical value of 2.33. Let's pretend that we don't remember the critical value, otherwise this question will be really quick. So if we're looking for the test statistic of 3.21, that's about here. The p-value is this area. It's the area, in this case, to the right of the test statistic. And here's how you find it. We're going to use the standard normal distribution chart. So use the z-table to find the area, in this case to the right, of z equals, our test statistic was 3.21. Now remember, your table, your standard normal distribution table or your z-table gives you areas to the left. So this p-value, if we wanted area of z to the right of 3.21, we'd have to do 1 minus the normal distribution, the area of z to the left of 3.21. And if we look that up on the chart or use your graphing calculator, I believe you get 0.9993. So our p-value is 0.0007. So the black area you see over here shaded in, this area right here, that is our p-value. Now you can tell from the graph, but it's easy to see here that the p-value places us in the critical region again. And if we're in the critical region, we reject the null hypothesis. Let's say that critical region, let's say that p-value had been bigger. So let's say the p-value had been, I don't know, not 0.01. Let's say it had been 0.1. We would have this value here. That also resides outside of the critical region. So in that case, we would fail to reject. Whoa, there we go, H naught. Okay, so here's the main idea of this. If our p-value is smaller than alpha, that means that we're in the critical region, so we reject. Wow, I keep leaving out the C. We reject H naught. If the p-value is bigger than alpha, then we fail to reject the null hypothesis. Okay, let's do something else. Let's do another one. I want to summarize this really quickly. The p-value, the probability of getting at least an extreme as the value representing the sample data. If the test is one-tailed, like say for example p is greater than 0.5, that right-tailed test we've been doing, then the p-value is the area to the right of the test statistic. If the test is left-tailed, so one-tailed but less than, then it's the area to the left of the test statistic. Now let's change our example just a little bit. Let's change it to this. Let's suppose that the claim is now instead that the likelihood of having a girl after using the XORT method just changes your likelihood of having a girl, not makes it greater or less, just changes it to something different. So now what we would have in this case is a two-tailed test. We would have p is not equal to 0.5, so the opposite would be p equals 0.5. And if you remember from our section on hypothesis testing and stating those, the statement that has the equality in it is always the null hypothesis. And the statement that does not have the equality in it is the alternative hypothesis. So since this doesn't have a greater than or less than, it just has a not equals to, what we have in this case is a two-tailed test. Oops. Okay, in this problem, they would like us to calculate the p-value. So we're going to find the p-value here. Now this is the same z and same alpha that we had before. So we're still going to use z equals 3.21. The p-value is still going to be calculated, at least at the first part, by using our standard normal distribution table. So remember, the probability that z is bigger than 3.21 was 1 minus the probability that z is less than 3.21, which is 1 minus 0.9993, which gives us 0.007. I missed a 0 there, didn't I? 0.007. Now this area is this region over here. If this is the z value 3.21 for our test statistic from our data, and that's the region here, that area right there is 0.0007. However, we have another one, because this is a two-tailed test, on the left-hand side. So this region over here, starting at z equals negative 3.21, which I'm not graphing very well, is also an area of 0.0007. So in a two-tailed test, we have to combine these two. You can either think of it as adding them together, or the total p-value is going to be 2 times 0.0007, or 0.00014. Okay. Now notice again, since this is smaller than alpha, then we would be in the critical region in both cases, so we reject H naught. Okay, so let's summarize that. If the test is a two-tailed test, so p is not equals to, say, 0.5, then the p-value is twice the area to the right or left of that test statistic. Okay. A quick summary on what we just did. We have two different methods for determining the validity of a test statistic. Of a hypothesis. The first one is this, the critical value method. In the critical value method, you have your alpha and its corresponding critical value. So let's say we're doing a one-tailed test. This region over here has area alpha, and it has a corresponding critical z-value. In the critical value method, we're going to, let me change colors here, we're going to compare this to the test statistic from our data. So let's say our test statistic puts us here. And then in that case, we're in the critical region. And if you're in the critical region, you always reject the null hypothesis. On the other hand, if your test statistic is over here, then you're not in the critical region, in which case you would fail to reject the null hypothesis. I strongly recommend that you do a quick sketch of the bell curve and plot your alpha and your critical value, and then you can compare this test statistic pretty easily. The second tool for assessing this is not the critical value method, but it's also it's the p-value method. So if we're doing, in this case, the p-value method, again, you'll have your alpha. You may or may not have your critical value, but you would use the test statistic from your data to find its p-value. And if your p-value is smaller than alpha, wow, that's not an alpha. Alpha, that means, say this is alpha, and remember that, alpha isn't that. Alpha is this area. If your p-value is smaller, then it's more extreme. So then we would be in the critical region and we would reject the null hypothesis. On the other hand, if the p-value is greater than your significance level, then you have some part of it that is outside of the critical region, then you would fail to reject.